So in the last couple of videos, we've been looking at areas where motors of different kV and different voltages perform the same. So we've been looking at a smaller slice of the range of performance of each motor. So let's take a quick look through the same motor, but see what the differences are when you actually increase the voltage and increase the kV. Because that is the really common thing you want to do. You want a faster motor to get more power, but what does that actually mean in terms of the measurements that we're doing? So we're looking at that same motor, the Tornado T1 1407, and this is the 2800 kV, and we're on 3S. And as usual in this chart, we're looking at torque and RPM, and the color is efficiency. And each of these little bands is one particular throttle range. So this one here at the end is 100% throttle, and this shows us what RPM it gets to almost unloaded. And then as we apply heavier and heavier load, the motor slows down, it uses more current, and it produces more torque. Now for a quad in the air, the torque requirement of the prop, we can't like force it to use more torque. And it's going to follow just kind of a curve that's shaped just kind of like this. And we'll look at some prop data at the very end. So we're going to be kind of, the performance of the motor that we're actually using is going to be this stuff here on the lower end of the chart. Now, as we go up in kV, what do you think we're going to see from this chart? As I increase the kV, is the torque, the maximum torque that we measure, is this going to be lower? Is the RPM just going to raise? Are we going to get a skinnier triangle down like this with less torque and higher RPM? Is the torque going to go up? Will we get more torque at lower RPM, but our total RPM won't not changing? Thankfully, it's actually a lot simpler than that. As I increase the kV to 3600 kV, you can see we just get kind of an extra pie slice here at the end. All of the performance that we had in this low range is all the same. Anywhere that we were able to make torque before, we can still make torque even at the higher kV. We haven't lost any torque at the high end, and we haven't lost any RPM on the low end of the chart. We just get an extra band of performance here off the end. So if I toggle back, you can see that's the 2800 and that's the 3600. So what this would do if we have a propeller on here, like let's say our torque curve runs up through here, this is where we run out of thrust at full throttle. We can't get the propeller needs more torque to push past the end, but we don't have any more torque to give. This is as much torque as we can get at 100% throttle. So when we go to 3600 kV, all of a sudden we have more torque available at higher RPM, and now at full throttle we're up here. So we're getting more RPM, we're getting more thrust out of the propeller. And if I switch now from the 3600 to the 4100 kV motor, you can see basically the same thing happens again. Between these two, it's not quite as straight a jump. You'll notice that this seems to be a lot more slanted. So while the kV is increasing and the peak RPM that we're hitting is increasing, the amount of torque that we're getting on high loads at high throttle is not increasing as much as it did from 28 to 36. You'll notice 28 to 36, there's a nice kind of even chunk up on both sides, and if we go up here we get a little more at the top but a lot more at the bottom. Now most of this is like nowhere near any of the power we're going to use. Our propellers are mostly going to be kind of down in this range here for this kind of size of motor. So we actually do see a lot of this performance if we're down here just around 30,000 RPM. When we go to the 4100 kV, now we're getting up to, nearly 35,000, which is a very significant increase in thrust. But the other kind of interesting thing to note about this is the torque curve of the prop is fixed. You can't force torque into something. So at low RPM, the propeller is only going to need so much torque to spin at low speed. And similar to how like volts and amps with electricity, you can't force amps through something if you don't change the voltage. a device can only pull amps into it. The propeller isn't going to, you can't force torque into the propeller. The propeller just will require a certain amount of torque to spin a certain speed. And as long as you're spinning that speed, that's all of the torque that you can possibly use for it. So it doesn't matter which of these KV motors I select, if our torque point for, just a low RPM hover is right down here, all of them can hit it. Something that you'll hear people talk about a lot about is low end torque, and how much torque your, a bigger motor or a more powerful motor will feel, at the bottom of the sticks. And we can see, well, you can't push torque into a prop. So what could that possibly mean? Even if we did have higher loading at lower RPM, all of these motors are performing just about the same. We can hit very high torque values at all of these KV. Nothing in here is sagging or drooping. So what does that mean? Well, what I think people are feeling is, remember that each of these lines is one throttle position. So this line here is 100% throttle, and this is 50% throttle. And as I go up in the KV, the 100% throttle, we still have just as many throttle steps. There are still 20 individual throttle steps that we're looking at each of these charts. But if you look at just these ones here on the bottom, as I go lower in KV, they get thinner and closer together. So kind of intuitively, as you go up in KV, you're essentially losing throttle resolution. If you want to hit this zone at very low torque and very low RPM, on the low KV motor, you have like nearly twice as many throttle steps to hit that one particular point of thrust, where on the 4100 kV you blast right past through that, and the same point on your throttle, if this is where you're holding your throttle stick, by just changing the 4100 to the 4100 kV motor, all of a sudden that same position, now you're way up here, which, if you follow the torque curve of a prop, is at higher torque value and making a lot more thrust. So that low end torque feel, it's not that the motor is actually performing any different. All of these motors, the efficiency has changed, but all of these motors are capable of producing that torque at all of these RPM values down here. But when you have the high kV motor, you're pushing straight past through all of the lower thrust areas just even faster. So it would be the equivalent of putting like some negative expo on your throttle. You zoom up through the low torque sections of the motor quicker, just because a 10% throttle command is going to move you even further up into the power band of the motor than it does on the lower KV motor. So that's KV. What happens if we change the battery voltage? So right now we're looking at the 4100 kV motor on 3S. If we drop this to 2S, what happens? Do we lose torque off the top of the chart? Or do we lose just RPM off the end of the chart? Well, of course, changing the voltage is very much like changing the kV, and we just lose another slice of the pie. So going from 3S to 2S, again, all of this range of performance down here is available in both both voltages at this kV. Changing to 2S, we haven't lost any torque off the top of the chart here, or any RPM off the middle of the part. We've just lost this one slice off the end. And now our 100% throttle that was up here is now down here, where about 75% throttle on the 3S test. And of course, really interesting, if we compare the 4100 kV on 2S with the 2800 on 3S, which are mathematically, if you multiply the expected RPM for both of those KVs, they're the same. And so the motors perform almost exactly identically. So we're within a theoretical like 300 kV difference or something like that. And you can see that basically, in terms of torque and RPM, now remember the efficiency is changing because the 4100 kV motor happens to be is less efficient, But anywhere along this line here, our full throttle point, a torque value that we hit here, we're going to hit the exact same torque value at the exact same RPM on the lower kV motor with higher voltage that we are on the higher kV motor at lower voltage. So while the efficiency is different slightly between the two, when you throw a prop on these, both of these motors with the same prop are going to hit the same RPM and give you the same amount of thrust. Now, the efficiency difference that we're seeing here, remember, it's not due to the kV, but we have a couple of competing factors. So this particular 4100 kV motor is testing less efficient than the other motors in the lineup. And we know that going to a lower voltage gives us a boost in efficiency. So we have a less efficient motor with more efficient voltage, and it happens to be just slightly worse than the more efficiently constructed motor with the higher voltage. So if this motor was built to the same efficiency standard, shall we say, as the 2800 happened to be, then we would see higher efficiency in this one because we get just the boost from the low voltage efficiency, and we wouldn't have the penalty from the construction on the winding efficiency. And of course, we really want to look at the high kV motor on high cell count. So let's go to 4S, and you can see just how far all of these throttle steps are spaced apart from each other now, and we're hitting insanely high RPM, over 60,000 RPM unloaded, compared to down on the 2S where we're only breaking just barely above 30,000. And similar also to when we were looking between the 3600 and the 4100 kV, if we look between the 4100 on 3S and on 4S, you'll notice that the extra pie slice here at the end isn't completely even either. It does seem to be biased a lot more towards RPM and less towards high load torque. So it looks like the motor is struggling at very high loads, at very high throttle as we increase the kV and the voltage on it, but it certainly has no problem spinning very freely at very low torque loads. So if you have a prop that's very light, you're going to get a lot more benefit running this 4100 at 4S. You've got a lot more room to grow. And this can also be a good benefit in the air. Even if we happen to have, say, a prop that's say our torque curve on our prop takes us up to here, prop unloading is going to reduce the load on the motor, and so that's going to push prop unloading is going to push your load down into this side of the graph. So you're going to get a bigger benefit from the higher kV, the free spinning high kV motor here, where prop unloading is going to have slightly less of a big effect on the RPM you're capable of getting with, on the 3S or the 2S, because you're not constrained as much on the high load side of things. So as it unloads, you're not seeing as big a spin up from the RPM increasing there. And finally, this is just the 100% throttle run of all of the motors at all of the voltages here that we've tested. And I have some torque curves of a couple of props plotted as well. So I have the 4100 kV motor at 2S, 3S, and 4S, the 3600 kV motor at 3S, and the 2800 kV motor on 3S and 4S. The props, we've got the Racecraft 3076, which was a nice kind of middle ground prop, the Rotorex 3045, because how could you not, and the Racestar 3035 Pro, because that was a fairly terrible prop that had really heavy loading. That's this blue line here. So you can see the difference in load between all of these different props. The 3045 is actually really low load, which is great because that's, its efficiency is really good. We get lots of thrust out of it, and it's low load, so it pushes us into more efficient area on the motors, where the Racestar prop didn't give us a tremendous amount of thrust, and you can see the loading is a lot higher, so it's going to take more power to get spun up. And you can also kind of get a sense of what sort of performance difference you're going to see from each of these changes in motor and change, either increasing the voltage or increasing the kV. Anywhere where these lines cross each other, so where the prop line crosses this 100% throttle motor line, is basically what RPM and torque you're going to hit in a static bench test. And I don't have data on these props that extends up in there, but you can kind of get a sense of the trend line and see that the torque requirement of these props is going to continue curving up like this, and so you can kind of guess where it's going to cross even the high kV high voltage. You know, we can kind of assume like the Raystar prop is going to cross kind of somewhere up like that, and the Rotor X prop is probably going to be down a little more like that, higher RPM. This bottom section here, these two are almost identical, and so of course these are the 2800 kV on 3S and the 4100 kV on 2S. The same charts that we looked at that were almost identical to each other before, and you can see there where the prop line is crossing, well, both of them at the same place, and so both of them are going to have identical performance. The very, very top, of course, we have the 4100 kV at 4S, and you can see how big of a jump that each of these kind of classes has to each other. Like going to that 4100 kV 4S, you get a really, really big increase in RPM. And if we had an even lighter prop, I mean, the 3045 is a pretty free spinning prop in the first place. So you can expect that you're not going to get, you know, we've got these areas of higher efficiency down lower. We're not going to be anywhere near that because our freest spinning prop is only down here, kind of in the middle of this this torque range. Probably the only way that you would see RPM quite that low is if you had like a 3020 bi-blade prop or something like that, but most of the 3-inch props tend to be tri-blades, and so I don't know of anything that spins that freely that's not a T-mount, which is you know, for a smaller class of motor. In the middle section, we've got, well, all of the middle options. That's the 3600 on 3S here at the bottom, the 2800 at 4S in the middle, and the 4100 on 3S just right above. So while these aren't all exactly the same, they are going to be very, very similar in performance, with our little 4100 on 3S taking just a bit higher in basically all of these tests. But it also does give you a bit of a sense of where the heavier loading is making a smaller and smaller difference. So this Rotor X prop is going to see a much bigger benefit between the 3600 and the 4100 because this kind of gap is bigger than our heaviest prop here is got a much smaller gap into that as the torque kind of falls off at a high loading. And of course, as you continue out to the extremely high kV and high voltage, you can see how that narrows even further, where we have a much, much larger gap up to there. And while these tests certainly are not super precise in judging the efficiency, you can also get a bit of a sense for what efficiency bands at full throttle that we're looking at on these different motors as well. You know, all of these kind of middle options, they're very, very similar, although the slightly highest efficiency overall is going to come from the lowest voltage of the three, because this is a 4S test, and this motor just happens to not be manufactured quite as efficiently as the other, and so we see a little bit more benefit in that 3600 3S test. And you can also see where that Raystar is going to pass, you know, where all three of these props are in this same efficiency band, this you know, area is 10% efficiency. The Raystar, because it's going into much higher loads, is going to cross down into a lower efficiency band than either of these other ones, where the 3076 is going to skirt that edge and just be right on the edge, and the Rotor X is actually still going to continue to pass into this efficiency band for much, much higher RPM. And if you go all the way up to that high voltage, high kV, that heavy loaded prop is going to drop massively, where where the equivalent efficiency zone from there is the one up here. So this is going to jump 1 to 20% efficiency to get to this torque value there, where if the rotor X is probably only dropping back 1, if it lands up in here, and if the 3076 is somewhere up there, then it's maybe dropping 1 in a little bit. So your not just your efficiency, but your total current draw is going to be better on these lighter loaded props that fall into the efficient zone, where the efficiency on this heavily loaded prop, as you start loading the motor way down, is going to get worse and worse and worse.